This time we're going to talk about our point of view or our camera in the three-dimensional space in computer graphics. So what we're going to set up is simply a data structure that represents where we are or where our point of view is and where it's looking and how it's oriented, how it's rotated, and how it's set up. We're gonna look at setting up ways to move this around, both incrementally and also by simply setting it up from scratch each time. And finally, actually in the next lecture, we're going to look at the lens of the camera, the width of the point of view and other things when we actually project things onto the screen. But for now, we're just going to look at things that have to do with the model view matrix, which are the position of the camera and its orientation, and how we can set this up and how we can put the data that represents this position and orientation of the camera into the model view matrix to use in our calculations there in the OpenGL pipeline. So here's an image of the viewing volume. This has more to do with the projection itself, which we'll talk about next lecture. But this is kind of the idea. This is the thing that we're moving around. We imagine that we have a near plane, which is what we're going to be projecting onto. We have a far plane, which is, well, we can imagine it as something we're projecting from, but mainly it's just the furthest thing that we actually draw something on. And we clip everything away that's further away. And when we look at depth calculations, we'll see the reason for this actually being there. Then on the near plane, we see this little imagined screen, which has this height and width ratio. And the angle is something that we can use to compute the points, the XY points on the near plane that we're going to be projecting onto. More on that in next lecture. For now, this is the OpenGL function that sets this. So GLU perspective, taking in this angle, the aspect ratio, and the near and the far plane. For now, however, we're going to be looking at the position and the orientation of the camera. And here we have this utilities function, gluLookAt. If we're using that, we can send in the X, Y, and Z coordinates for the position of the camera, the eye. We send in X, Y, and Z coordinates for a point that we're looking at, which we call center. And the X, Y, and Z coordinates for an up vector. If we're not using GL utilities, if we're using a different version or implementation of OpenGL, if we're using a later version of OpenGL, then this has to do with, then we can just use the calculations that we're going to go through here, set them up ourselves, and set up the matrix in a different way. Either way, the calculations themselves are relevant and what we need in order to set up the camera with this type of data. So here we're setting up OpenGL with the model view matrix, which is the matrix that we use here. We usually begin by calling this function before we start calling the local transformation functions. So GL matrix mode GL model view, then load identity. So we start with a clear model view matrix, and then we call gluLookAt, which will set this up for us. So to look at the actual data that we're going to be using, we can imagine that some kind of base camera is positioned in 0, 0, 0 and looks along the negative z-axis. And in the end, this base camera is what we're going to be using to project onto. So what we need is a way to take our arbitrary camera that is positioned anywhere and oriented in any way, looking at anything, and to transform that and the world along with it, all our scene along with it, into the base camera. That is to take our coordinates and represent them locally in the camera's own coordinate frame, making the camera the center of the universe, and thus making everything set up for the base camera, positioned in 0, 0, 0, and looking along the negative z-axis. So we want a way to set up this coordinate frame for the camera, and then when we set up this coordinate frame, we want a way to move it around, point it in any direction, rotate it incrementally about itself, slide it along its own axes, and so on and so forth. gluLOOKAT can set up this coordinate system for us, this local coordinate frame, but if we want to have more control over the camera, we're going to want to actually do this ourselves and set the model view matrix ourselves in order to do the incremental changes rather than always have to build the coordinate system or the coordinate frame for the camera from scratch. So here we have this local coordinate frame of the camera, where we have the point of origin for this coordinate frame is called I, and then we have the u, v, and n vectors, which are basically the x, y, and z axes for this local coordinate frame. And there in the background we see the actual base coordinate frame, base coordinate system. And we want to make a transformation that takes this local coordinate frame and sticks it into that base camera, or takes coordinates represented in the base camera and gives us the coordinates as represented in the camera's local coordinate frame. Just two ways of saying the same thing. So this is our imagined transformation, or the transformation that we're going to do. We want to take this u, v, n, and I coordinate frame, and we want to rotate it and translate it so that it basically sets exactly into the base coordinate system. And if we set up a transformation that does that to the camera, that same transformation will take all the rest of our scene and put it in front of the base camera. So we're never actually performing this transformation on the camera itself, but instead we're making a transformation that would do this to the camera. Then we're applying this transformation to everything in our scene, all the vertices that we set into the OpenGL pipeline. And in that way we will take them as they're represented in front of the camera and instead transform them so that they're in front of the base camera. Or take their coordinates as they are represented globally and represent them instead locally in the camera's coordinate frame, making the camera, in either case, the center of the universe and the main point that everything is relevant to. So we're going to look at what gluLOOKAT actually does, what the math is behind gluLOOKAT when it does this transformation for us. So we have to start by making these vectors u, v, and n. We simply have these points, I, and the lookat point, or the center, and then we have this vector up, which is basically an anchor for what direction is generally up, but it's not actually the correct v vector, or the up vector that's straight up from the camera, but instead an approximation of the general up direction in our scene. So we need to use these three points and vectors to make this entire coordinate frame. So the first thing we can do is to simply say n is the same direction as the vector from the eye to the center point, except n should actually point backwards. So we can simply take the difference between those points, I minus lookat, or I minus center, and that would be our n vector. We always have to remember that a program will have to normalize these vectors before it'll continue. When doing this on paper, we can save the normalization for later, but but the normalization is important. These have to be unit length vectors, and u and v at all times must be unit length vectors. So the vector u, that is straight to the right, we can take a cross product of the n vector and the up vector. So the up vector isn't the actual correct up vector, it isn't perpendicular to n, but it anchors our kind of nv plane, or the zy plane for the camera, so that we know that if a vector is perpendicular to up and perpendicular to n, it'll be straight to the right from the camera, or from the point of view, or the viewer. So u equals up cross n. Now we have two of our vectors, they're perpendicular to each other, and by taking their cross product we'll get the third vector that's perpendicular to them as well, finishing up our coordinate frame. And remember that the point of origin of our coordinate frame is the I point itself. So then we have a point of origin and three vectors for a coordinate frame. So finally v equals n cross u, and then we have all the data. So here's just a nice image showing these calculations. So now that we have the coordinate frame itself, we need a way to put it into the model view matrix so that so the model view matrix multiplication will actually do the transformation that we want it to do, which is take the coordinates as represented in the global coordinate system and represent it in the camera's local coordinate frame instead, to make the camera our new center of the universe. So this is done, as you can see here, and this is basically the inverse matrix of a matrix that would be ux, uy, uz, and 0 on the first column, and then v on the second column, n on the third column, and simply I, the point I, on the fourth column, which would be basically 4 columns, each representing one vector, and the last one representing the point of origin. This is the way we set up our usual local transformation matrix, local coordinate frame transformations, except in that case we're taking our coordinate representation from the local coordinate frame to the global coordinate system. In this case we're doing it the other way around. We're taking them from the global coordinate system and representing them in the local coordinate frame. So by taking the inverse matrix of what we'd otherwise do, we're doing it the other way around. So this is the matrix we set up. After that, we take the other type of local coordinate frame transformations and add them all to the right of this matrix, in a sense mixing together the two things, the viewing part of the model view matrix and the model part of the model view matrix, mixing them together on the fly, so that in one matrix multiplication we do the whole thing. We take the coordinates from our local drawing coordinate frame to the global and to the local coordinate frame of the camera, all in one matrix multiplication. So model view matrix is basically viewing times model, where M is the matrix describing the coordinate frame of our 3D world, of our the local coordinate frame that we're drawing into, where we want to take our drawing space and translate it to and scale it and rotate it. We multiply this matrix V to the left side of M, or what we actually usually do is we start with V and then we multiply the parts of M to the right side. Doesn't matter which way we think it. Then we're adding these two transformations together. So we're basically doing two local coordinate frame transformations in one. So now that we can set this up, what we actually want to do is kind of do local increments or local changes, incremental changes on the camera itself. We might want to slide it along its own U, V, or N axis, basically saying go straight forward to the camera, not meaning along the Z axis of the global coordinate system, but along its own axis. We might want to rotate it around itself, either by looking up and down, rotating around the U vector, looking to the sides, rotating around the V vector, or rolling to the sides, much like a plane that's taking a turn, rotating around the N vector. So in order to do this, we really no longer use gluLOOKAT, but instead we set up the calculations ourselves, and then we keep track of what the last local coordinate frame for the camera was when we're using it. We keep track of this, and every time we start drawing, we build the coordinate frame for the camera again, or we build the model view matrix again from the coordinate frame of the camera. And every time changes are made, every time buttons are pushed that decide that the camera should be looking up or looking down, or whatever it is that controls the motion of the camera, every time this happens, we do incremental changes to the camera's coordinate frame, and the next time we draw a new frame, this new changed coordinate frame will be used to build the model view matrix, and thus the motion of the camera will be incremental throughout the frames. So sliding the camera, that's fairly simple. If we want to slide it along the U-axis, we simply say we have this factor that we want to slide it by, then we simply multiply that factor by the x, y, and z coordinates of the vector u, and add those respectively to the x, y, and z coordinates of the point of origin. Thus we're not changing the vectors, we're not changing the orientation, we're only changing the position, but we're doing so in a controlled way, controlled by the vectors of the coordinate frame itself. And this is what it would look like in a program. In this case, we're taking a factor for u, v, and n into the same function. So if we're only going to move forward or backward, we'll simply say send 0 into the delta u and delta v variables, and only have whatever factor it is that we need in the delta n. So a little bit more complicated is to rotate the camera, but that's not so complex when we actually look at the fact that if we're rotating around one vector, we're actually not going to be changing that vector, but only changing the other two vectors relative to each other. So the rotation around an n-axis would basically happen in the uv plane, and this uv plane will then affect, basically they'll affect each other, the u and v vectors, but the n vector will be unchanged. And we can see how this would look. Here we basically take the cosine of the angle that we're going to turn about, and we say the new u vector will be the cosine times the old u vector plus the sine of the old v vector. The new v vector will be the minus sine times the old u vector and the cosine times the v vector, and we'll get this rotation. Finally, we can do the same type of rotation, except switch out v for n or switch out u for n, and then we'll have rotations in about the other two vectors in the same way. Finally, of course, the new u vector and new v vector have to be actually overwritten onto, or have to actually overwrite the original u and v vectors. So in a program, it should look like this. So yeah, this would be basically what the functions for rotating around V and U are usually called. So rotating around N called roll, around V called yaw, basically looking to the sides, and pitch as if steering a plane up and down when we're rotating around U. And these functions can be made in a similar way to the roll function. So that's it for position and orientation and incremental changes and updates on the camera and everything that has to do with the model view matrix part of the camera. So next lecture we're going to look at perspective transformations and actually projecting our 3D scene onto a 2D screen and all the calculations that have to do with that. Thank you.